Starting in 3. Greetings and welcome. Today we're going to talk about solving systems of linear inequalities. So we're going to be working in 2 dimensions, right? 2 variables, x and y, and talk about these systems. Now, first of all, let's just do a quick little recall, I guess, of just straight up graphing. I guess, well, for one, we need to remember how to graph, and 2, we need to know how to graph a linear inequality. So let's graph the following. What if I have, well, actually, I'll even put it in an ugly form for us. How about 2x minus 3y is less than or equal to, we'll make that a 6. How about there? So if I want to graph this, one of the things typically that we'll attempt to do is I often put it in slope-intercept form. Slope-intercept form I find is often an easy way to graph for me. So slope-intercept form is y equals mx plus b. All right, so this is a sloppy intercept form. Bam. Right? And in slope-intercept form, we have m is your slope. All right, rise over run, and b is your y-intercept. All right, so that's would be like 0 comma b would be the point on the coordinate plane. So I'm going to try to put this into slope-intercept form. So basically the key factor here is it's solved for y. So I want to get y by itself. So if I want to solve for y, what should I do to both sides? Eventually. But the first thing I'll do is subtract 2x. Technically you could divide by -3 first, but I like to try to do my order of operations in reverse, and it usually ends up a little easier to do the work. And now I would divide by -3. And let's see, first thing we have to remember here about inequalities is that when you multiply or divide by a negative, what happens? Correct. So we have to flip the inequality. So this is now, instead of a less than or equal, it's going to be a greater than or equal. All right, so now this is in slope-intercept form. And let's see, we'll make a little note to ourselves. When mult slash div by negative, flip the inequality. All right, and that's every time. All right, so now that I have it set up like this, what is the slope and what is the y-intercept? What do we got? Yep, so 2/3 is the slope and the y-intercept is -2. So that means I'm going to be going up 2 units and over 3 units, right? Because that is rise over run is the idea for the slope. It's often the terminology that we use. So let's graph this. Actually, I'm gonna. Oh man! I almost just closed the very window that I'm writing in. Alas. Let's see. Let me hide this. Bam. I'm just making a little grid in my graphing software here. I just deleted it, you silly Mr. Y. Oh, what? How's that deleting it? Oh, I should hide it. That's why. Command H is the hide button. So I'm just going to steal this little grid for myself. Like that. Bam. And paste this just so I have a nice little grid. But I'm not looking for fancy grids. You've perhaps seen mine before. I'm just looking, just draw your line, and a couple little tick marks, stuff like that. It is important that your tick marks are relatively evenly spaced. Otherwise, they won't land. Your graph won't be proportional. It'll have a whole bunch of like time warps in it, essentially. So let's see. So how do I graph this? I know my slope. I know my y-intercept. Where should I start? What should I do? Yeah, so I'll start at the origin and go down to the y-intercept. So that's at -2. And so there's -2. And now what do I do? Yeah, so up 2 units and over 3 units because the slope is 2/3. And there's another point on my line. And I could actually even repeat this process up 2 over 3 and hit another point on my line. Now actually another interesting thing is that 2/3 is the same as -2 over -3, right? Because those minus signs would cancel out. So I also could go down 2 and backwards 3 if for some reason that benefited me. Sometimes it will, like if my point was way up in the corner and I can't fit up 2 over 3, maybe I could go down that number and back. And that happens to also be on the same line. Let's see, so yesterday we were making fun of Khan for drawing poor lines on this. Let's see if I can do any better. And actually, first of all, I want to point out, this is a solid line. There's a couple other facts to know from this symbol here. So greater than or equal to told me 2 things. All right. First of all, the equal to tells me that it's a solid line. Secondly, the greater than part, what do you think that's going to have me do? Yeah, I'm going to shade above this line. All right? Because if you look at this equation, I'm saying y is greater than this line, right? So I'm looking for all solutions that the y coordinate is bigger than that, right? So here's the y-axis, here's the x-axis. So what y values are larger than this line? Y is the vertical variable, right? So I'm having a vertical relationship here, and it's saying what points are greater than, so vertically speaking that would be above, all right, is what I'd be interested in. So it turns out for this, every point above this line is a solution to this system. Well, actually this isn't even a system yet, this is just a single inequality. I could even do a check, and usually the best point to pick is the origin, 0, 0. So the origin, right, 0, 0. So as a check, is 0 greater than or equal to 2/3 times 0 minus 2? Is 0 greater than or equal to -2? Yeah, it is. So it seems like I at least have a point in the correct spot. I mean, it doesn't verify that my line was right or anything like that, but I do have a point in the correct direction. So that's how I typically will be graphing an inequality. I use the slope-intercept form method. Yesterday we saw what's called the intercepts method. All right, it's different than slope-intercept method, where basically you plug in 0 for y, and then I'd have 2x is less than or equal to 6, and I'd solve for x, and I'd get x is less than or equal to 3. And notice that my x-intercept is at 3, right? And then I would plug in 0 for x and solve for y. So plug in 0 for x, this whole thing would be 0. I'd have -3y is less than or equal to 6. I'd divide both sides by -3. I'd get y is greater than or equal to 2. Sorry, -2. And notice that my y-intercept is -2. So by plugging in 0 for one variable and solving, you'll get one of those intercepts. And then plugging in 0 for the other variable and solving, you'll get the other intercept. And then you can kind of draw the line in between them. But I'm a fan of y equals mx plus b. I find that to be a little bit more interesting. One more quick concept I guess I'll do is, what does the graph y is less than 2 look like? And what does the graph, I'll even do this in a different color, x is greater than or equal to -3 look like? So y is less than 2. What could you tell me about that line? Any facts? So what is okay, so what kind of line is this? It's horizontal. Isn't the y-axis vertical though?
Yeah, but it's at that same point.
Right, if I had the line y equals 2, I would be looking at this line here, right? Right. The other way I could think about this is y is less than 0x plus 2, and I could say, aha, the slope was 0 and the y-intercept was 2, right? So 0 slope is a horizontal line, right? So if I graph this, all right, here's the y-intercept at 2, and it's going to be a horizontal line. However, this less than sign tells me what? What kind of line is it going to be? Solid or dotted? Dotted, because it doesn't include the equal to, right? It doesn't include the points itself. It's everything up to it. And then y is less than. Y is a vertical variable, so less than should be an above or below comparison. So which way is less? Below, right? That's good sound effects. Now, trickier is x is greater than or equal to -3. That's a vertical line, and that is the only kind of line that can't be put into slope-intercept form. What if I asked you what the slope of that line was? What would you even say? No? That would... actually, this doesn't even have a y-intercept, technically. For a vertical line, it actually has no slope, which no slope is different than zero slope. All right, no slope or undefined slope is another way it's said. So let me show where this is. So -3 on the x-axis is here. All right, it's a vertical line. It includes the equal to, so it'll be a solid line. All right, something like that. Yeah, I'm not that pleased with that, but last try. Yeah, that was the worst of them all, but that's fine. So it's a solid line, and if I ask you the slope of this line, you'd say, oh, it's going up 1 over 0. Or no, maybe it's going up 3 over 0. Or up 1,000,000 over 0. But putting slope like that, you can never divide by 0. This is undefined, right? So that's why the slope is undefined for a vertical line. Now, the other thing with a vertical line is, how do I figure out what way to shade this? Do I shade it above or below? Well, yeah, above or below is not a good question to ask, because this is my x variable. It's a horizontal comparison that I'm making here. So horizontally speaking, greater than is to the left because the positive to the right, because the positive x-axis is to the right, the negative x-axis is to the left. So greater than, it's not an above or below question when you have an x that you solve for, it's a left or right question. So this is what I'd be looking at right here. Okay, so horizontal, vertical lines, those are a little bit tricky. Now it turns out, notice how I graphed both of these on the same coordinate plane? That's essentially what we're doing today. And if I had this as a system, I would say that the solution set is everything in here. The overlap between both of those, all right, is what the solution of the system would be, okay? So it would be a dotted line up top, it'd be a solid line here, and it would be everything inside, and it would go in those directions infinitely, right? So, so let's actually get to some real examples here. I just wanted to make sure some of these, you know, what was I just going to say? I was just about to say premediate skills, but that's not a word. Prerequisite skills would have been. That's funny. Anyways, let's get to the real beef of this chapter. So let's see. Solve the system of inequalities. By graphing. So let's get a system here. So let's say I have x is greater than or equal to 0, y is greater than or equal to 0, and let's have 2x plus y is less than or equal to 4. So if I want to solve this by graphing, let's see, I'm going to get a little grid here. I'm guessing that because x and y are both greater than 0, I'm going to be in the first quadrant only. So that's why I'm choosing that as my kind of area of focus for my window there. Let's see. I know how to graph this first one. I know how to graph the second one. The third one I can't graph in its current form because it's not in y equals mx plus b form, slope-intercept, unless I want to use intercepts method. What method are you guys most comfortable with? Slope-intercept form or... Yeah, we'll just keep rolling with slope-intercept form then. So that'll be the first thing I'll do. I'm going to put all of these in a form that I can graph. So I'll have y is... Oh wait, let's see. Do I have to flip this inequality sign? No. Subtracting something is fine. It's multiplying or dividing by a negative. That's when I got to flip it. So let's see. So I've got 1, 2, 3 equations. Let's graph these. So x is greater than or equal to 0. That'll be my blue line. How do I graph that? What kind of line is that? What can you tell me? Solid line. Where is it found? It's on the y-axis. It crosses the x-axis at 0. Yeah. And it's a solid line. And it is vertical. So that's one of the things that for horizontal and vertical lines, right? X-axis is the horizontal one, but an equation x equals a number is vertical. So it's kind of the way I memorize it is I just memorize it. It's always the opposite of what I would first think. And that's how I memorize it, right? So it's like, oh, that's what I would have thought first. But there we go. So x is greater than or equal to 0. Which way would I shade this?
Would you shade it?
Shade it to the right.
To the right. Greater than would be to the right. I'm not going to shade it just yet, but I'm going to keep that in mind. Let's see, for my y equation, that'll be my purple one here. Y is greater than or equal to 0. What's that look like? Solid. Horizontal, and it passes through the y-axis at 0. So something like this. What's the slope of this line? 0, because I'm going up 0 over 1, up 0 over 1, right? And the y-intercept was also 0. Technically, the blue line had infinitely many y-intercepts, which is kind of funny. And which way would I shade this? This is a greater than or equal to symbol. It's related to the y, so I would shade this above. So currently, my common shaded region would be the whole first quadrant. All right, the common solution between just those two. Now throw this third inequality into the mix. I might make this one this orange color here. What can you tell me about this line? Well, actually, let's gather some more information about it. What other facts do I know? I know it's solid because of the equal to part, right? Which way is it shaded? Slope is -2. -2 over 1 if you're a real fan of rise over run concept, but -2 I like. B is 4, our y-intercept. Which way do I shade it? Below, because its y is less than something. So I'm going to shade the points below. Less than in a y relationship, y comparison would be below. Okay, so here we go. So let's graph this. So y-intercept is 4, so I start up at the y-intercept. And I'm going to go down 2 over 1, right? Down 2 over 1. And those would land on other points. So it looks like here and here. It's a solid line. And it's shaded below. Right? So the blue line was shaded to the right. The purple line was shaded above. And the orange line was shaded below. Now, don't just assume that because we have a little triangle, that the solutions will be inside the triangle. All right? You actually do have to analyze the shading of all of those in order to know for sure, because it's also possible, sometimes you'll have a solution like this, where it's just an unbounded region that goes forever, but its boundaries are like here, here, and here, right? And then it just goes infinitely far that way. So it could have been, you know, kind of everything in the first quadrant except that triangle. So just be aware, like, don't just assume that it's always going to be the inside of the shape. Now, one of the things we're going to do today is not only graph these, right? So my solution set is the infinitely many points within this region, right? So for instance, 1, 1 is a solution in there. And what I'm saying is that 1, 1, if I plug 1 in for x and 1 in for y in all three of my original equations, that it will be true for all of them. All right? If I plugged in this point over here, this would have been true for the blue and the purple, but not the orange. Okay? This would have been true for the blue. Actually, it looks like it would have just been true for just the blue. This would be true for the blue and the orange, but not the purple, right? So you can see that there's points that, right, this would be true for the purple and the orange, but not the blue. So there's points that could be working in 1 or 2 or most, but not all. And we're interested in the ones that work in all of them. So let's actually just consider this point 1, 1 mentally anyway. If I plug 1 in for x, is 1 greater than or equal to 0? Yes. If I plug 1 in for y, is 1 greater than or equal to 0? Yes. If I plug 1 in for x and 1 in for y here, 2 times 1 is 2, plus 1 is 3. Is 3 less than or equal to 4? Yes. So it appears as though I'm in the right spot, right? So that's kind of an idea. You can do a check, but you'd have to check it in all three. Now, today what we're going to do is, let's say that these variables represented something within a word problem. Let's say x is the number of tables that I make, and y is the number of chairs that I make in a day at my handmade furniture chair factory, okay? And I told you that there's no such thing as antimatter tables, and there's no such thing as antimatter chairs, right? So I'm just saying, hypothetically, x is tables, number of them, right? And y is chairs, number of chairs. Right, so that was the first two facts that I had, is I can't make a table out of antimatter and have it count as a negative number of tables, right? Because I'm not that talented yet. I haven't learned that skill. And then I had some other constraint based off of maybe this was all about my lumber resources. Maybe I have 4 pieces of lumber, and I told you that a table takes up 2 pieces of lumber, and a chair takes up 1 piece of lumber, whatever that lumber, maybe like a whole tree or something like that. And every day I wake up early, I cut down 4 trees, and then I make some furniture. So it's possible I could make 0 tables and 4 chairs, right? And I'd use up all my lumber just having 4 chairs, right? And that would be true for all of those. It's possible I could make 2 tables in a day and 0 chairs, right? If y was 0 and x was 2, right? 2 times 2 is 4, and that would work out, right? So I'd have all sorts of different constraints. But then let's say I throw in an additional fact for us. What if I told you I had a profit equation? P of x comma y is going to be my profit equation, where I've got 2 inputs that tell me my profit. Let's say that I earn, I don't know, let's say I charge $100 for every table, and I charge $60 for every chair. And now I'm just not interested in, am I actually within my, thresholds for kind of possibility within my problem? Am I, I can't make more tables and chairs than my supplies allow, or different things like that. I could have multiple constraints. But now I'm not just interested in what are the possible solutions. I'm interested in what's the most profitable solution, okay? And there's, like I said, there's kind of infinitely many points here. I've as a result of my problem made them more finite. I mean, I would only be able to consider the ones that land on the grid because I can't have a half of a table, arguably. So I would be interested in kind of like these points that I just plotted. But of these points, chances are, if I want to get an extreme value, a maximum value for profit, it's probably not going to be the one in the middle, right? Because the one in the middle is playing it safe. Like, it's not doing the extreme thing. It's not using up all of my resources, right? If I make one table and one chair, I only used up 3 of my trees that day, right? So that's probably not going to give me the maximum profit, all right? If I made, so it's chances are it's not going to be a point within the triangle. Now let's consider the points on the edge of the triangle. Would it be maximizing profit if I made 1 chair and no tables? Probably not. Probably not. Or 2 chairs and no tables. Or 1 table and no chairs, right? Chances are the points that are on the boundary are also not going to maximize or bring me to my most extreme values, right, for my profit equation. So it turns out the solutions that I'm most interested in are going to be the corners of whatever my shaded region is. All right, the vertices, right? A vertex is kind of the corner of a polygon. Vertices is plural for it. And that's the idea, is I want to target what these vertices are. All right, so what are the coordinates of these vertices? Let's see. I'm going to label this A, B, and C. So what is point A? What are the coordinates of point A? Right there. X, Y, what's that? 0, 0. What are the coordinates of point B? 0, 4. And what are the coordinates of point C? 2, 0, right? So those are the points that I'm interested in, and I'm actually going to plug those in order to find out which one gives me the most profit. So let's figure out what is P of 0, 0. 100 times 0 plus 60 times 0. What's that going to equal? $0. So chances are waking up this morning and being like, I don't feel like making any tables or chairs. I'm not going to make any money that day either, right? So it's not going to maximize profit. Maybe that's not the most important thing to me. Maybe I just want to sleep in, but that's not what I'm trying to maximize, the number of hours of sleep, right? I mean, I suppose I could have had an equation regarding the number of hours of sleep I get and maximize that if that's what was in our interest of maximizing. But let's see. So then 100 times 0 plus 60 times 4, if I plug in the 4-chair situation here, 60 times 4, 100 times 0 is 0. 60 times 4 is going to be $240. And then let's figure out P of 2 comma 0, so 100 times 2 plus 60 times 0, and that's going to be $200. So what's your advice for me if I want to maximize profit? Make, what was the Y value? Y was chairs. So my recommendation is make 4 chairs and no tables. To get a maximum profit. Of $240. Right? So maybe my conclusion is, hey, I should shut down my table production and just close that whole portion of my factory because I'm in the chairs business now. It's just going to be Waddy chairs is all I sell. I'm not going to be Waddy woodworking and furniture or whatever. It's just Waddy chair factory because that's where the money's at. I mean, clearly there's probably some limitation to just like an all-chair economy. I imagine that at some point people will need tables. But within the limited constraints that I defined, that would be my optimal solution. All right? And mathematicians will oftentimes be hired out by companies to analyze all sorts of different constraints, like what are their material limitations, what are their man-hour limitations, what are the restrictions on each product. How much money do you make from each product that you manufacture? And they'll consider all of these variables and balance all of them out and then figure out, okay, this is the constraints. These are the possible boundaries, right? And it might be like some crazy weird polygon or something like that. And they'll look at this and figure out what is the solution that's going to be either maximum profit or minimum cost, right? Or minimum loss of life, right? Whatever the situation might be, whatever you happen to be optimizing, that's what you would be considering. So the thing that I want to point out, now you guys kind of just believed it off of instinct that the extreme points would make the most sense, and you were right, that does make sense. But there's something called the Vertex Theorem, which kind of says exactly what we just did. It says the maximum or minimum, the max or min value of some equation, like a profit equation, or it could be a cost equation. Maybe you're trying to minimize that. F of xy equals ax plus by plus c on a polygonal convex set. Now that's a weird set of words. Convex set occurs at a vertex. Man, my writing is getting worse. Of the polygonal boundary. Bam. Which is kind of what I said there in not so many words. Or maybe more words, they were just different words. So maybe I didn't minimize the number of words I used, but perhaps maximized the understanding of the phrase that I used. So I used more words, but perhaps words that were more familiar to us. So what it means by polygonal convex set, that's talking about our shaded region, our triangle, our octagon, whatever crazy shape we happen to have. That's a polygonal convex set. And it occurs at a vertex of the polygonal boundary. Basically, it's saying it's going to happen on one of the corners. Now, there are some situations where there will, instead of being an optimal solution, you can actually have infinitely many solutions where, let's say, both B and C were equally optimal. Okay? If I was actually charging $50 or earning $50 per chair, I think I actually would have had a tie between both B and C, right? Because 4 times 50 would have been 200 and 100 times 2 would have been 200. Sometimes it can occur that you'll have a tie between two vertices, and basically what that will mean is any point along that whole boundary will end up being equally optimal, all right? And that only occurs when there's a tie. But most of the time it will end up being just exactly one of those points, all right? Let's see. So, man, this video is getting crazy long. I really want to fit another problem in here. I might end up recording just a separate video explaining another problem of this in a moment, but I think this is a sufficient explanation for now. So I'm going to say goodbye to our internet friends. Bye-bye.